Okay, good morning, students. So, in today's class, we are discussing about the series and parallel circuits. Series and parallel circuits. So, here first we are discussing about the series circuits and then go for parallel circuit. So, first one is the series circuit. Okay, so first, what is meant by series circuit? So, generally, a series circuit is one in which the several resistance are connected one another. So, such connection is called as series connection. So, here we have to see in different elements of the circuits are connected in series. So, first one is the resistors are connected in series and inductors are connected in series and capacitors are connected in series. So then what is the formula to find the equivalent resistance, equivalent inductance and equivalent capacitance? So in general we have to remember that in series circuit always there is a same current and different voltage. Same current and different voltage. So just remember this, in series circuit there is always same current and different voltage will be there. So first just check resistors are connected in series. Resistors are connected in series. So see here, so let us consider any three resistors. Suppose this is the resistor 1 and this is the resistor 2 and this is the resistor 3. So all these three resistors are connected in series. So resistor 1 is the R1, R2, R3. These three are the resistors which are connected in series, and the combination of these three resistors are connected across a voltage source V. So this is the voltage source V, positive, negative. So initially we are taking three resistors and the three resistors are connected in series, and the combination of these three resistors are connected across a voltage source V. So here the voltage across the resistor R1 is suppose V1, and the voltage across resistor R2 is suppose V2, and next one is the voltage across resistor R3 is suppose V3. So here the voltage across resistor R1 is V1, across resistor R2 is V2, and across resistor R3 is V3. So here this is the series circuit. So for series circuit always there will be same current and different voltages. And here we are assuming some current will be flowing through these resistors. Suppose here I am assuming the current I. So I is the current flowing through R1, R2 and R3. The common current will be flowing through all the three resistors. So here this is the current flowing through, I is the current flowing through three elements, that is three resistors R1, R2 and R3. So here the total voltage V is equals to V1 plus V2 plus V3. But according to Ohm's law, according to Ohm's law, we know that. So here the value of V1 is equals to I into R1, and V2 is equals to I into R2, and V3 is equals to I into R3. You just substitute all these three values in the above equation. So here V is equals to V1. First V1 means that is the I into R1 plus V2. V2 means that is I into R2 plus I into R3. So here the value of V. So how can we find V? So V is equals to total current I into R equivalent. So substitute that also, I into R equivalent is equals to I into R1 plus I R2 plus I R3. So on LHS side that is the same, I into R equivalent. From RHS we take I as a common. So then we get R1 plus R2 plus R3. So here I cancel. Therefore R equivalent is equals to R1 plus R2 plus R3. So this is the formula to find the equivalent resistance when three resistors are connected in series. So here when three resistors are connected in series, the formula to find the R equivalent is equals to R1 plus R2 plus R3. Suppose n number of resistors are connected in series, then R equivalent is equals to R1 plus R2 plus R3 plus so on up to Rn. So this is the formula for R equivalent when three resistors are connected in series. And next one is the this is for the resistors are connected in series. This is the first, and second one is the inductors are connected in series. Second one is the inductors are connected in series. So here also we need to find the total inductance, that is the L equivalent formula when different inductors are connected in series. So here also let us consider any two inductors. Suppose this is the inductor 1 and this is the inductor 2. So these two inductors are connected in series. So here inductor 1 is represented by L1 and inductor 2 is represented by L2. And the current flowing through inductor 1 is suppose I1 and the current flowing through inductor 2 is we are assuming I2. So here different current will be flows here. Through inductor L1 is I1, through inductor L2 is current I2. So also let us assume the voltage across inductor 1 is suppose VL1 and the voltage across inductor 2 is VL2. So this is the for inductance. So just draw the equivalent circuit. So here this is the inductor. So here inductor 1 is represented by L1, inductor 2 is represented by L2, but in equivalent circuit we are taking that as a L equivalent. And here the voltage drop across inductor 1 is VL1, voltage drop across inductor 2 is VL2, and here we just take VL. And here the current I1 and I2 through L1 and L2, but here we are taking only the current I. So here these two inductors are connected in series. So already we are discussing in series always there will be same current. That means here I1 is equal to I2, that is equal to current I, but there is a different voltages. So different voltages means VL is equals to VL1 plus VL2. So we just substitute the values of VL1 and VL2 and VL. So here where the value of VL1 is equals to L1 into di1 by dt and VL2 is equals to L2 into di2 by dt and VL is equals to L equivalent into di by dt. So these VL1, VL2 and VL values should be substituted in this voltage equation, that is VL is equals to VL1 plus VL2. So substitute here. What is the value of VL? VL is equals to L equivalent into di by dt is equals to next VL1. What is the VL1? L1 into di1 by dt plus VL2 is L2 into di2 by dt. But here see here this is the equation. So here I1 is equal to I2 equal to I. That means in place of I1 and I2 we just substitute the value of I, because in series circuit there will be always same current will be flows. So in place of I1 and I2 we just replace by I. So that is L equivalent into di by dt is equals to, so L1 into di by dt plus L2 into di by dt. So the LHS is L equivalent into di by dt equals to, from RHS we can take di by dt as a common. So then we get di by dt as a common, then L1 plus L2. So here di by dt cancel. Therefore L equivalent is equals to L1 plus L2. So this is the formula to find the total inductance, that is L equivalent is equals to L1 plus L2 when two inductors are connected in series. So here also suppose n number of inductors are connected in series, then L equivalent is equals to L1 plus L2 plus so on Ln. So this is the formula to find the equivalent inductance when two inductors are connected in series. And next one is the capacitors. Next one is the capacitors are connected in series. And third one, capacitors are connected in series. So here also consider any two or three capacitors. Suppose I am taking two capacitors. This is the capacitor 1 and this is the capacitor 2. So here capacitor 1 is represented by C1 and capacitor 2 is represented by C2, and the current flowing through capacitor 1 is suppose I1 and the current flowing through capacitor 2 is I2, and the voltage drop across the capacitor 1. So here the voltage drop across the capacitor 1 is VC1 and the voltage drop across the capacitor 2 is VC2. So this is the general diagram. For the we have to draw the equivalent circuit also. This is the capacitance. So here we are taking C1 and C2, but here we are taking C equivalent. And here we are taking current I1 and I2 through C1 and C2, but here we are taking only I. And the voltage drop here VC1, VC2, but here only we take VC. So here I1 is equal to I2 equal to I, because it is a series circuit. In series circuit always there will be same current. So I1 is equal to I2 equal to I. But it is a different voltage will be there. So different voltages means VC is equals to VC1 plus VC2. So here the values of VC1 and VC2 and VC should be noted. So first one, the value of VC1. VC1 equals to 1 by C1 integration of minus infinity to T I1 into dt. And second one is the VC2. VC2 equals to 1 by C2 integration of minus infinity to T I2 into dt. And last one is the VC. So VC value, VC is equals to 1 by C equivalent integration of minus infinity to T I into dt. Again substitute this value of VC1, VC2 and VC in this equation. So the equation implies first one is the VC. What is the value of VC? 1 by C equivalent integration of infinity to T I into dt is equals to VC1. What is the value of VC1? VC1 equals to 1 by C1 integration of minus infinity to T I1 dt plus next VC2. What is the value of VC2? 1 by C2 integration of minus infinity to T I2 into dt. So again from this equation in place of I1 and I2 we just replace I. So then the equation will becomes 1 by C equivalent minus infinity to T I into dt is equals to 1 by C1 integration of minus infinity to T into I into dt. Here I1. So in place of I1 we just replace by I. Next plus 1 by C2 integration of minus infinity to I into dt. Here also it is the value of I2, but in place of I2 we just replace I. So then the equation will becomes 1 by C equivalent integration of minus infinity to T into I dt is equals to from RHS. What we are taking common? So integration of minus infinity to T I dt is common. Integration of minus infinity to T I dt is taken as a common. Then we get 1 by C1 plus 1 by C2. So this value are cancelled. Then 1 by C equivalent is equals to 1 by C1 plus 1 by C2. So this is the formula to find the total capacitance, that is C equivalent when two capacitors are connected in series, that is 1 by C equivalent equals to 1 by C1 plus 1 by C2. Here also suppose n number of capacitors are connected in series, then 1 by C equivalent equals to 1 by C1 plus 1 by C2 plus and so on 1 by Cn. So these are the series connections. So initially we are taking resistors are connected in series. So when resistors are connected in series, then we get the formula R equivalent equals to R1 plus R2 plus R3 when three resistors are connected in series. And next one is the inductors are connected in series. So here we get L equivalent equals to L1 plus L2 and so on. In case n number of inductors are connected in series, then L equivalent equals to L1 plus L2 plus so on Ln. And third one is the capacitors are connected in series. Here we get the total capacitance 1 by C equivalent equals to 1 by C1 plus 1 by C2. Suppose here also the n number of capacitors are connected in series, then 1 by C equivalent equals to 1 by C1 plus 1 by C2 plus so on 1 by Cn. So this is the series circuit. And next one is the parallel circuit. So in the parallel circuit also we are discussing about the same parallel resistors are connected in parallel, inductors are connected in parallel, and capacitors are also connected in parallel. So next one is the parallel circuit. So here also we are taking first one, resistors are connected in parallel and inductors are connected in parallel and capacitors are connected in parallel. First one is the resistors are in parallel. So just take any three resistors and which are connected in parallel. So let us consider this is the resistor 1 and this is the resistor 2 and this is the resistor 3. These three resistors are connected in parallel. So this is the resistor 1, R1, R2 and R3, and the combination is connected across a AC, across a voltage source, DC voltage source, that is V. So here the current drawn from the source is I. So when this current I reaches to this point, it can be split into three parts. So one is the current I1 which is passing through R1, and second one is the current I2 which is passing through R2, and third one is the current I3 which is passing through R3. So you just remember here this is the parallel circuit. So in parallel circuit always there is a same voltage and different current. So in series circuit always there is a same current, different voltage, but for parallel circuit always there is a same voltage and different current. So here this is the total current drawn I, and it can be split into three different parts, I1, I2, I3, which is passing through resistors R1, R2 and R3. So here the total current I is equals to I1 plus I2 plus I3, and the voltages, but voltages will be same. V is equals to V1 is equals to V2 equals to V3. So where V is the total voltage and V1 is the voltage drop across resistor R1 and V2 is the voltage drop across resistor R2 and V3 is the voltage drop across resistor R3. So we need to substitute in this here equation, that is I1, I2 and I3. So here according to Ohm's law, we know that I1 is equals to V by R1 and I2 is equals to V by R2, comma I3 is equals to V by R3. And what about the I? I is nothing but that is V by R equivalent. So substitute all these values in this equation. So then we get I. I means that is V by R equivalent equals to I1. I1 means V by R1 plus I2 means V by R2 plus I3 means V by R3. So LHS is same, that is V by R equivalent. From RHS we just take V as a common. So then we get 1 by R1 plus 1 by R2 plus 1 by R3. So V cancel, therefore 1 by R equivalent equals to 1 by R1 plus 1 by R2 plus 1 by R3. So this is the formula to find the equivalent resistance when three resistors are connected in series. That is 1 by R equivalent equals to 1 by R1 plus 1 by R2 plus 1 by R3. Suppose n number of resistors are connected in parallel, then 1 by R equivalent equals to 1 by R1 plus 1 by R2 plus 1 by R3 plus so on up to 1 by Rn. So this is the first one, that is resistors are connected in parallel. And next one is the inductors are connected in parallel. So again let us consider inductors are in inductors are in parallel. So let us consider any two inductors. Suppose this is the inductor 1 and next one is the inductor 2. These two inductors are connected in parallel. Inductor 1 is the L1 and inductor 2 is the L2. Current flowing through inductor 1 is suppose I1 and current flowing through inductor 2 is I2. And the voltage drop across inductor 1 is suppose VL1 and the voltage drop across inductor 2 is VL2. So again draw the equivalent circuit for this. Here we are taking two inductors, but for an equivalent circuit we are taking only single, that is L equivalent, and the current flowing is I. Here we are taking I1 I2, but for equivalent we are taking only I. But here voltage of VL1 and VL2, but here only VL. So it is a series circuit or parallel circuit. So here inductors are in parallel, that means parallel circuit. So parallel means there is always same voltage, that means VL is equals to VL1 and VL2, but there is a different current. Different current means I is equals to I1 plus I2. So here what is the value of I1 and I2? So here the value of I1 is equals to 1 by L1 integration of minus infinity to t VL1 dt, and next one is the I2. I2 is equals to 1 by L2 integration of minus infinity to t VL2 into dt. And next total current I. Total current I is equals to 1 by L equivalent integration of minus infinity to t VL into dt. Now substitute all these three values, that is I1, I2 and total current in this equation, that is I is equals to I1 plus I2. So what is the value of I? I is equals to 1 by L equivalent equals to infinity to t. So VL into dt is equals to I1. What is the value of I1? That is 1 by L1 integration of minus infinity to t. So VL1 into dt plus 1 by L2 into integration of minus infinity to VL2 into dt. So again here, so here VL1 VL2 is equals to VL. So in place of VL1 and VL2 we just replace VL, because it is the same current. In the series circuit there is the same voltage, that's why in place of I1 and I2 we just replace I. But here in parallel circuit there is always same voltage, so in place of VL1 and VL2 we just replace VL. So then the equation will becomes 1 by L equivalent integration of minus infinity to t VL into dt is equals to 1 by L1 integration of minus infinity to t. So here VL1 that is represented by that is replaced by VL dt plus 1 by L2 integration of minus infinity to t VL2 is also represented by VL into dt. So therefore 1 by L equivalent to integration of minus infinity to t VL into dt is equals to, from RHS we take common, that is minus infinity to VL into dt is taken as a common, minus infinity to t VL dt. Then we get 1 by L1 plus 1 by L2. So this will be cancelled. Therefore 1 by L equivalent is equals to 1 by L1 plus 1 by L2. So this is a formula to find the total inductance, that is 1 by L equivalent equals to 1 by L1 plus 1 by L2. In case the n number of inductors are connected in parallel, then 1 by L equivalent equals to 1 by L1 plus 1 by L2 plus 1 by L3 and so on up to 1 by Ln. So this is the inductors are in parallel. And next one is the capacitors are in parallel. Capacitors are in parallel. So again let us consider any two capacitors. Suppose this is the capacitor 1 and this is the capacitor 2. So these are connected in parallel. So capacitor 1 is represented by C1 and capacitor 2 is represented by C2, and the current flowing through capacitor 1 is suppose I1 and the current flowing through capacitor 2 is I2, and the voltage drop across capacitor 1 is suppose Vc1 and the voltage drop across capacitor 2 is Vc2. So then draw the equivalent circuit, and this is the capacitor which is represented by C equivalent, and the current flowing through is I and the voltage drop is Vc. So it is a parallel circuit. So parallel circuit means there is always same voltage. That means Vc is equals to Vc1 that equal to Vc2, and it is having different currents. So I is equals to I1 plus I2. So here we know to substitute the value of I1 and I2. Here the value of I1 is equals to C1 into dVc1 by dt, comma I2 is equals to C2 into dVc2 by dt, comma I is equals to where C1 C2, here C equivalent equals to dVc by dt. So substitute all these equations in I equals to I1 plus I2, that is I1. First I, what is the value of I? I is equals to C equivalent into dVc by dt is equals to I1. I1 is the C1 into dVc1 by dt plus I2. I2 is the C2 into dVc2 by dt. So again in place of Vc1 and Vc2 we just replace by Vc. So that equals to C equivalent into dVc by dt is equals to C1 into dVc by dt plus here Vc1 in place is replaced by Vc. Again C2 into dVc2 is the Vc by dt. So from RHS again we take dVc by dt as a common. So then we get C equivalent into C equivalent into dVc by dt is equals to dVc by dt is taken as a common from RHS. Then we get C1 plus C2. So these two are cancelled. Again we get C equivalent equals to C1 plus C2. So this is the formula for total capacitance when two capacitors are connected in series. That is C equivalent equals to C1 plus C2. Here also suppose n number of capacitors are connected in parallel, then C equivalent equals to C1 plus C2 plus so on up to Cn. So these are the series and parallel circuits and different formulas: total resistance, total inductance and total capacitance when they are connected in either series or parallels. Okay, thank you. So remaining classes will be discussed in next class.